In this video, we are going to discuss the line integral of a vector field. So suppose that we are in R3. Okay, let me just draw roughly, just a rough sketch of R3. So that's the z-axis, x-axis, y-axis. And suppose we have a curve here. Okay, and let's label the curve C. Okay, so that's our curve C. And suppose that we have a force field. Suppose that we have a force field F. Okay, so we have a force field F that is continuous on this curve C. So suppose that we have a force field F that is continuous on the curve C. So obviously the force field F is basically, it's just a vector field. It is a vector field that represents a force. So this force field is continuous on our curve C. Okay. Also, suppose that we have the unit tangent vector field, the unit tangent vector field of C. So we say we also suppose that we have the unit. Okay, let me write the unit. Let me write unit again. Suppose we have the unit tangent vector field T. Okay, so this is the unit tangent vector field T on C, on the curve C. So what basically T does is it gives you the unit tangent vector at any point on C. Okay, it'll give you the unit tangent vector at any point on C. That's what T does. So we've got F, which is the force field on C. It's continuous on C. And we also have this unit tangent vector field T on C. So now, to define the work done by the force field F on C, we do it as follows. Okay, the work done by the force field F on C is defined as follows. All right, so now we define the work done by this force field. Let's write the work done by this force field. Okay, the work done by this force field F on C is defined by the following. So we're going to denote this work done by this force field F on C. We're going to denote it with a W. So we denote it with a W, and it's given by the integral along C of F dotted with T with respect to the arc length. So that's what defines the work done. Okay, that's the work that the force field F does on C. It's defined as this integral. All right. So based on this definition of the work done by this force field, we then go further. All right, we go further. Suppose this now. Suppose that the curve C has a parametrization. Okay, so suppose the curve C is parametrized. Suppose that the curve C is parametrized by this position vector. Okay, R of T. All right, where where the parameter t ranges between a and b. So suppose that C is parameterized by R of t, where t ranges between a and b. Then in that case, we can express our work here. We can express this integral in terms of this parameterization. Then we can write t, which is this unit tangent vector field on C. We can write it as follows. We can write it as R prime t divided by the norm of R prime t. So we can write this unit tangent vector field in this way. Write it in terms of this parameter of C. Okay. Also, we can write ds, our arc length here, we can write it in the following way. We can write it as the norm of R prime t dt. So we can write it in this way. So now we can then go ahead and express our work integral in terms of this parameter. All right, so we can say, therefore, we can now say the following. We can say that the work is equal to the integral. We know that it's equal to the integral along C of the force field F dotted with the tangent, with the unit tangent vector field T with respect to the arc length. Now, this is the same as the following. So this is equal to the integral from A to B of our force field, if expressed in terms of the parameterization. So we express the force field in terms of the parameterization, and of course we dot this with the following. So we replace the t with R prime t over the norm of R prime t multiplied by ds, which is basically R prime t with the norm of R prime t, that is, with respect to t, or dt. So we can do this. We can express the integral in this way. So obviously, now you're going to cancel out. You're going to cancel out the top here and the bottom here. So you're going to cancel out this. You're going to cancel out with this because they're the same, right? So you cancel those two out, and this leaves you with the integral from A to B of f of R of t dotted with R prime t dt. Okay, so obviously R prime t dt, you can write that as dr. You can write it as dr. It's the same thing. So now this is the same thing as the following. It's the integral from A to B of f, okay, of R of t dotted with dr of t. It's the same thing. So now you can write, finally you can express the integral as follows. You can express it as the integral along C. You can just write it as follows. The integral along C of f dot dr. So you can finally just write it like this. So now this is basically how you can express the work done by this force field. This is how you can express the work done by this force field F on C. You can express it in the following way. Okay, you can express it in the following way. Now, what you're gonna do now is that you're gonna use this this expression for the work done by this force field. We're gonna use this result in defining what a line integral, or what the line integral of a vector field is. Okay, so we use this expression to define the line integral of a vector field. All right, so let's write here definition. Okay, definition, we're going to define the line integral of a vector field now. So to define this, we're going to say, suppose that Okay, suppose that F is a vector field. So suppose that F is a vector field. Suppose that F is a vector field. Okay, continuous, a vector field that is continuous. Okay, a vector field that is continuous on a curve C. Okay, on a curve C. So F is a vector field that is continuous on a curve C, right? That has parametrization. Okay, that has. So this curve C has parametrization. Parametrization. R of T, where T ranges between A and B. Okay, so suppose that F is a vector field continuous on a curve C that has a parametrization R of T, which is where T it ranges between A and B. In that case, we say then the line integral of F on C. We say then the line integral of F on C is given by the following. So now we're defining the line integral of a general vector field on any curve C is given by the following. So the line integral of F on C is given by the following. It's given by this integral. Integral along C of F dotted by dr. That's basically how you define the line integral of a vector field F on a curve C. So we're using the result that we got for work above. And of course, this integral, you can express it as follows. As the integral from A to B of F of R of T dotted by R prime T dt, which is also the same as the integral along C of F dotted by T ds. So that is basically how you define the line integral of a curve. Well, not of a curve. That's how you define the line integral of a vector field F on a curve C.